Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we are going to continue our journey towards data models, in particular validation of JSON and XML. The overarching goal is actually data frames. Who has already heard of data frames? Pandas. Okay, now you know where that comes from, at least the theory of data frames. But first we need to validate JSON and then everything will just fit together. Another question for you, who has already seen a rack for real? A pile of nodes. Who never saw a rack? Okay, we need to fix this. This here is a rack. So after the course, come and see it, and you will see there's a pile. Of course, it's an audio-video rack, but it's exactly the same thing. So then you will have seen one. All right, just remember that. So this is where we left last time, and I told you, do not confuse well-formedness and validation. Well-formedness means you can open the document, parse it, and build a memory representation of the document, a tree, right? And it's really a tree in the sense of a data structure, right? You have a tree in memory. You might have, of course, a lot of bells and whistles, like maps in some nodes to accelerate looking up the children and so on. But this is the idea, right? So well-formedness means you're able to create the tree for every document. Validation is another question you can ask, but only if you have already been able to build the memory representation. So only if it's well-formed, all right? And another aspect is that validation depends on the schema you provide, right? It's your intent to have the data look like following a specific structure. So I told you about oxygen. And so the idea when you validate is that, so at first it looks like just a yes/no question, right? Either it's valid or it's not valid, right? It's following the schema or it's not following the schema. But as we will see, there is something else that can happen when you validate, and that's called annotation. Annotation is just the idea that once you have established that a document is valid against a specific schema, we will see that it involves data types. You might actually go ahead and cast the types to these, right? Because you might remember that in XML, we just have text, right? It's only text, characters inside the elements. And if the schema says this is an integer, then what's going to happen is that in the memory representation, you're going to replace that text with an actual integer, like 32-bit or maybe big integer in Java and so on. The same goes with all the other types, Booleans, dates, and so on and so on. That's called annotation when you do this, right? So you see that thanks to the schema validation, the representation that we will have in memory will be actually even more fancy and elaborate compared to what you would get if you just parse for well-formedness, right? So we'll see that it's really going further in terms of memory representation. So validation is a yes/no answer, and annotation, typically done at the same time, is the fact that you replace the text with the actual types that you expect. Why? Because you want to query it later. And so if you already have the types as such, it makes it much more efficient. So I'm going to try to give you an intuition of validation, and then, of course, I'll move on to explaining to you JSON schema, and XML schema. The idea is this. Trees never come alone, right? They are like elephants. So you never have a tree just on its own. Typically, you have millions of trees or billions of trees in what we call a collection, right? A collection of trees. So you're going to have 1 million or 1 billion JSON documents or 1 million or 1 billion XML documents. The idea is that if you don't validate, these trees that you have in your collection might look very heterogeneous, right? They don't look alike, and there's all sorts of different trees of different sizes, of different depth, and so on. This is what you have. So of course, I just simplified with shapes and colors, but basically this is an example of a heterogeneous collection that hasn't been validated, right? On the right, you have a collection with 1 million or 1 billion trees, but they all follow a schema, specific schema. They all follow a specific structure. So here it's a homogeneous collection of trees, right? Now, why do we distinguish between the two? Because in the real world, this is what you often get. If you just collect data and log it, you're very often going to get this kind of data. However, when you apply, let's say, machine learning, like you want to apply a regression or whatever with a machine learning model, you typically expect your data to be more homogeneous, right? Who knows a bit of machine learning? Assume a lot of you, right? So you have the features, the labels, and so on. So you expect a bit of structure. So how do you turn this into this? It's very complex. It's a very wide area. It's about cleaning up and curating the data. And in that course, we are going to learn a bit how to do this, or having the tools to turn this into this, right? So it not only involves validation, it might also involve manipulating a little bit the data in there to make it look alike, and then followed by a validation, right? So that's the goal. And again, this is what real life gives you very often. And this is what you have at the end when you curated and cleaned everything up. All right, so you see, by the way, the contrast with relational databases, right? In a relational database system, you're only allowed to have this. Why? Because from the very beginning, you're asked to provide a schema right? In PostgreSQL and so on. You need a schema. You can only do this. This you will not manage to do in a relational database management system, because it's not possible to have a relational table if you didn't define a schema before. So this is new. This is specific to big data.
How connected?
Is there a question? Maybe we forgot to mute by default.
I muted the person.
All right.
But I can ask in the chat.
Was there a question?
I don't know. I will ask in the chat.
Yeah. Just need to be careful, because since we record. All right. So this was, of course, just with squares and colors, but of course we're dealing with data. So just to give you an intuition, this is messy data, right? It's typically data that hasn't been cleaned up. How do I see that it's messy data? Well, you see, it's only one object, of course, but even with one object, you already start seeing in the nested structure that something is not very clean. Here, B, the key B, has an array. Look at what there is in the array. There's a string, foo, a boolean, true, null, and an object. That's heterogeneous. You have in E an integer, and then an array of two integers, 3 and 4. That's an example of data that isn't quite, that is not easy to validate, let's say. It's not in a state that you could build a strong schema. This is, on the contrary, an example of data that's been cleaned up, where there is structure. How do you see this? Well, because look at this array C, right? It has 3 objects. The 3 objects have keys foo and bar. Bar is optional, but still foo and bar. And then foo is always associated with a string, and bar is always associated with an array of integers. This is the kind of document that's very easy to validate against the schema. It's very easy to build a schema that will validate against that document. And maybe you have millions of other documents that look alike and that will be valid against that schema. This here would be tougher, because you would need a very permissive schema. You would basically need a schema that says an array of whatever, right? But of course, this is going to be less efficient later. Who sees the difference between the two? That this is a bit cleaner and this is a bit messier? All right, very good. So this is the idea. And of course, this is now what we are targeting. We are going to focus on this kind of document in XML or JSON, and we want to enforce the structure so that any data we add in the future conforms to this. There are many different schema technologies, a lot of them. Even for XML, there's maybe at least 3 or 4 that are quite popular. In JSON as well, there are several. So of course, I'm going to teach you a few of them so that you get the idea, but it will be very easy to learn any other one. And the reason is there's a lot of commonalities that all of these technologies have. Right? We'll see that schemas are also related to data formats that we'll take a look at later. And my goal is to just make sure you have absolutely no difficulty learning them. And I have good news for you. Since they all follow more or less the same ideas, what I'm going to introduce to you now on data types as part of validation is general, in the sense that it applies to pretty much any validation language and format, right? So this is general. First, that shouldn't surprise you, because this is something we saw in JSON. When we look at data types, we can distinguish between 2 kinds of types: the atomic types and the structured types, or the complex types, right? Atomic types in JSON, if you look at the syntax, you kind of see them already, right? It's like strings, numbers, booleans, nulls. These are like, this would be validated as atomic types, and objects and arrays that would be structured types, right? It also shouldn't surprise you because who programs in Java? A little bit at least. Okay, so in Java, you know that there is also a distinction between they are not called atomics in Java, maybe they're called simple types, I can't remember exactly. But everything that is in short, byte long, Boolean, and so on, these are simple types. And then you have the objects, where you create the classes and instantiate the classes into objects, right? So these are the structured types. Just be careful about one thing. In Java, string is technically a complex type. It's a class, even though it's immutable. But in the context of databases, like this string is considered an atomic type. It's not considered a structured type, just so that you're aware that this is a difference with Java. All right, for whom is the difference clear between the two? Okay. So I'm going to go now through a menu of atomic type, but trying to keep it general, because again, more or less, it's going to be the same categories of atomic types you have everywhere. And since you already program, it should be no surprise to you. First, we have strings. You're computer scientists, so I don't need to explain to you what a string is. And they are here, but again, considered atomic types in the context of databases, right? All right, so a string is just a sequence of characters. All right. Then we have numbers. Good news is we also have, in particular, these 8-bit, 16-bit, 32-bit, and 64-bit integers, byte short, int long. They typically exist. Very often, you even have the signed version and the unsigned version, right? You know the difference. Signed means that you cut into negative, positive, right? But you only get half of the interval on both sides. And unsigned means you only take the positive ones, then you get the full, in the case of 32, for example, between 0 and 2 to the power of 32 minus 1. All right, but it's not all. You actually get more than that. Because in XML or JSON, you might remember that there is no restriction on the length of text or on the length of a number in JSON. And that means that in particular, it doesn't need to be an integer. It doesn't need to be 64-bit. In fact, you can have any precision and scale. You could have, I don't know, 1,000 digits and then a decimal point and then 1,000 other digits, right? Theoretically. And that means that when you validate, you typically have in many languages, in many schema languages, a way to accept this arbitrary precision, integers and decimals. So typically you have an integer type that accepts any integer of any length, just a sequence of decimal digits, right? That's interpreted as an integer. Then you have typically a decimal type that accepts anything that has digits with a point in the middle, so any decimal number. And some of them might allow you also to restrict the precision and the scale, right? In PostgreSQL, for example, you can restrict the precision and the scale. But there is a difference with PostgreSQL, because in PostgreSQL, you do have a limit on the number of digits you can have. There is an upper limit. But in the case of JSON and XML, there is no theoretical limit. The limit is basically the piece of software that you're using might tell you, okay, I'm not able to handle such big integers, but there is no limit in the spec. This is what is very important. It's really depending on the implementation. All right, so this is it. And so you typically have this arbitrary precision integer and decimal that accepts everything. And you also have typically you remember in Java float and double, right? It's this 32-bit and 64-bit IEEE 754. Don't ask me why I actually know that by heart, but that's basically the name of the standard that defines this. And you typically also have them in many schema languages. You might not have the two of them in every language. Some of the schemas will only expose double or floats. Maybe they will also call it differently, but that's the idea, all right? Okay. Then you have Booleans, true or false, which is an opportunity for me to say that you should be aware that there is the notion of the lexical representation of some data, right? So for example, in JSON, you will see TRUE, which is the lexical representation. But when you actually validate it and get a Boolean, then this is true. It's the mathematical true that you actually get. So be aware of the difference between the two. I will come back on that. Then we have dates and times. These are the ones that are often forgotten. When somebody designs a new programming language, they will think of the strings and integers and Booleans and so on, and they will forget about the dates and the times. But the thing is, if you work in a company, they are super important. You cannot do without them. Sadly, JSON doesn't have them in the syntax, but it's not a problem at all because if we use a validation language, we can have actually dates also in JSON. All right, then we have hours, minutes, seconds. We have also timestamps with a specific date ends time. Typically, we can go to the microseconds in many of the systems. We have time intervals. For example, 2 days and 3 hours, or 1 year and 3 months. There is only one thing to be careful about with durations or intervals, the same thing. Be careful about the separation between months and days, because there can be 30 days, 31 days, 28, 29 days in a month. So it means that if I tell you 1 month and 2 days, it's ambiguous. Was it February? Was it March? I don't know, but 1 month and 2 days, you cannot say unambiguously how long that is. So just be careful between a month and a day, but the rest is unambiguous. There's always 12 months in a year, 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. By the way, the name is sexagesimal, the base 60, just a piece of fun fact. All right, so these are the durations that typically you can also have types for when you validate in many systems. Then you can have the binary format. Typically here, you distinguish between the base 16 lexical representation, then you would have base 16 between 0 and 9 and A and F in JSON or in XML. And there is another representation of binary that is called base 64. Who heard about that one? All right, it's even more efficient. As its name indicates, it's actually based on a base 64 instead of base 16, with a pretty smart way of encoding things. All right, but again, it doesn't matter if it was hexadecimal or base 64 in the actual JSON or XML. Once you have parsed it and put it in memory, it becomes a sequence of bits, right? Because that's just a binary format. And then we have null, which typically exists on its own as a value. There are several ways to consider null. Actually, it's a bit of a mess in the way that people deal with it. There are people who consider that null is just a value that you can have in any type. Like in Java, for example, you have objects and the object can be null. Or you can consider that it's really a special value that is different from the others. There are systems that consider that null is the same thing as absence. So if you are missing a key in JSON, it's the same as the key with null. That's the case in MongoDB, for example. But if you want to be truly general, you need to be careful and make the distinction, right? So null is not the same as an absent value, and it's not the same as an empty string. That was discussed a bit on the forum. So in the most general case, these are 3 different things. By the way, we also have null in XML. I just didn't bother you with that, right? It's just called nil, N-I-L. But I didn't want to bother you with that. Okay, so that's something I already said. There is a difference between the value space and the lexical space. The lexical space is really the text that you see in JSON or XML before you open it. It's just a text file, right? And this is the sequence of characters that encodes the value. For example, if you want to encode the number 4, it might just be the digit 4, or it might be +4E0, which means times 10 to the power of 0, or it might be 100B if you accept it in base 2. These are all lexical representations, or literals is an alternate name for that, of the number 4. So on the right, you have the lexical representation. On the left, you have the value space with the actual 4, right? So this is the actual mathematical 4. So there might be several lexical representations for the same value, but the other way around, every lexical representation should give you exactly one value. And again, typically, when you validate, you forget about the lexical representation, and what you have in memory is the actual 4. So typically, you might have had this +4E0 in JSON. Once you parse it, you might have an int or a double or whatever in memory, but you don't have a string anymore. You don't have anymore this sequence of characters. For whom does that make sense? All right. So if you hear literal or lexical representation, this is what it means. It's the sequence of characters that are used in a textual format to write that value. This is the same for a date. For example, if you want to have August 1st, 2017, there's many standards about that. but one of them, which I think is ISO 8601, I'm getting worried I actually remember these things, 2017-08-01 is the lexical representation. So on the right, this is an actual sequence of characters, it's a string, and when you parse it, it becomes a date. And one of the ways that you could have this is the number of milliseconds since 1970, right? Which is what is done on many systems in order to encode dates and times. Okay, so this is it. And that's the same, I did the same for, this is now a timestamp. Typically especially in XML, which this standard is followed, you have a T in the middle, so the date on the left, the time on the right. Z is for the time zone GMT, right? So that's the Greenwich. And on the left, of course, you have the actual time, so the actual timestamp, right? I didn't tell you about time zones, but we have them also as part of many validation systems, right? So you can have a time zone or no time zone. Durations look like this in terms of lexical representation, typically in XML. So you have P, then 1 year, 2 months, T, 3 hours, right? For whom does that make sense? Okay, it's only a standard. It's one of the standards. There are many different standards, but this is one of them, and this is one that is typically followed in the XML schema validation. All right. And between, so we also have the concept of subtype and supertypes in many systems, and the idea is that you have a subtype when it's a subset of the value space. For example, the set of non-negative integers is a subset of the set of integers, and that means that the type non-negative integer is a subtype of the type integer. All right, so this is there is a hierarchy of types that we can have. All right, okay. So this is about atomic types, and again, that was general. I gave a few examples coming from the XML/JSON world, but this is really general, and in almost any system, you're going to have types like this. That was the atomic types. So now let me go to the structured types. Typically, there's 2 of them that are frequently encountered, and on an from an abstract perspective, it's maps and lists. So if you think of JSON, it will not surprise you because a JSON object is a map and a JSON array is a list, right? We also find them in data frames. Typically, I'm going to start talking about them. So a data frame struct would be also a map in the key value model, and a data frame array is going to be a list. On the side of XML, it's a bit different. It's not a one-to-one mapping, but basically the idea is that when you have attributes within the same elements that is logically like a map that matches attribute names to elements, even though when we drew the tree, we have a specific node for every attribute, right? But someone asked the question about this, and you could have an additional map to model how you navigate to the attributes. And then elements typically would be considered lists in the sense that every element has a list of children that can be elements of text or text. But don't forget that in XML, the elements can repeat, right? You can have multiple times the same elements at the same level, and that's okay. All right, so these are the structured types. If you have to remember one thing, remember the left side, maps and lists. And if you want to focus on one of them, focus on JSON, right? A JSON object is a map and a JSON array is a list. All right. Something else that is common to many systems, even though they don't do it in the same way, is the notion of cardinality. What do I mean with this? I mean that we have collections of trees, right? When we look at XML or JSON documents, we have collections of trees. These collections could have different sizes. It could be empty. It could be a collection of just one tree, or it could be a collection of 0 or more trees, or a collection of 1 or more trees, right? In the same way, when you have an array that contains values in there, the array could be empty, the array could have exactly 1 element, the array could have 0 or more elements, or the array could have 1 or more elements. And in order to model that, when you validate, we speak about cardinality, right? It's basically the expected cardinality. What do you expect in your data? And so in many languages, you have this way of saying exactly 1 or 0 or more, typically the clean star, 0 or 1 is the question mark, 1 or more is plus. If you, who knows regular expressions? Okay, that's one less thing to learn, because this star, question mark, and plus shouldn't surprise you, right? It's exactly the same idea. There are also sometimes adjectives. Who knows Google protocol buffers, protobufs? Nobody heard about protocol buffers. Okay, that's also yet another validation technology to more like a data format. And then they say required when it's exactly 1, repeated when it's 0 or more, and optional when it's 0 or 1. All right. This I'm showing to you at the request of your predecessors, so the students in previous years, because they asked me to give them some giant correspondence table with all of these types across several languages, just to have an overview. But the one thing, if you shouldn't be scared about that, the one thing you should notice is that no matter what you look at, it's pretty much all the same types, right? They're not called the same way, you know, but we're in Switzerland. We don't use the same words for Zurich-Deutsch, Ostschweizerdeutsch, Baseldeutsch, Berndeutsch, Walliserdeutsch, Embry, Embruf. So we use different words. It's exactly the same thing here. Just consider it like dialects. And we have a different name every time, but there is a correspondence. I'm going to take an example, maybe with, I don't know, double. So we have double. In JSON schema, they call it number. Then we have excess double in XML schema, double type in Spark SQL, so data frames in Spark SQL, double precision in PostgreSQL, and float in Python, right? So this is an example, but it's more or less how it corresponds. So you have all the atomic types, decimal, integer, byte, and so on. And then I put object and array on the last line. So you can see that an object is a struct in data frames or Spark SQL. We'll see it in a couple of weeks. An array corresponds to array type. In Python, somebody observed yesterday, and you were right about it, that it's the dicts, right, in Python that would correspond to an object. And we have lists here that correspond to arrays, right? In PostgreSQL, it's a bit more complicated. You can build composite types and so on, but I'm not going in the details, right? What I want you to see here is really the idea that the types, the list of types is more or less the same one. You just need to look up the documentation when you are unsure about how it's called, but it's pretty much equivalent. Just an observation that will simplify everything for you. This here in XML schema is the same as in JSON and JSONX. So this is exactly, it's the same standard, right? So this is all following the same one. Okay. You see also, if you look at JSON schema, that it doesn't have as many data types. It actually uses some very small list of types and adds some constraints in there, right? So just so you're aware that it works a bit differently. Is everybody following? Okay. All right, so I hope that this helps you to have just this correspondence table that should give you an idea. All right, now I'm going to move on to the first schema language, JSON, and then I'll explain JSON schema and XML schema. I used to only explain XML schema actually a few years ago, but since things are evolving in the direction of JSON, this is why now JSON is getting more and more to the front. What is JSON? Well, technically, it's something that I co-designed with a few colleagues for the purpose of teaching schemas. So because it's the simplest to explain how schemas work, it's very intuitive. And then you will see, you will just see by yourself. And then I explain JSON schema that is also popular. So here's how many of the slides now are going to look like. We have a schema in the bottom part of the screen, and we have an instance in the upper part of the screen. What do I call an instance? An instance is just a document you want to validate, right? So I have a document, last Einstein, that's the JSON document I want to validate. And below I have a schema that is what I expect. The first thing that you noticed is probably that the schema is also JSON. Right? That's the first thing. And that's very common. JSON schema is also going to be JSON. XML schema is going to be XML. It's not always the case, but here it's the case. And one of the particularities of JSON is that the schema looks a bit like the instance, which makes it intuitive, right? So in the schema, you say, I'm accepting objects that associates the key last with a string, and string is taken from here, right? It's just in the column here. So from all these types. So last is string, and the document above, is it valid against the schema? Who thinks yes? All right, it is valid against the schema, right? So this document it is well-formed first, and in addition to being well-formed, it's also valid against the schema. And I insist on against the schema. Valid is not absolute, it's always against the schema. Here's another one. I have an object now with two keys, last Einstein, first Albert, and in my schema says last must be a string, first must be a string. So my instance is valid against my schema again, right? Then we have, just now to go a bit more in depth, by default, if I say last must be a string and first must be a string, the keys are still optional. It's fine not to have them, right? They can be here. If it's here, it must be a string, but it's also fine not to have it. So it means that if I have this schema right here, the document on top is valid against the schema as well, because of, by default, all the keys being optional. You can require the key. In that case, you just add an exclamation mark in front, right? And here it says required last, required first. And now you must really have the two keys for it to be valid, all right? Of course, you can use other types. For example, here, last Einstein, age 142. Last must be a string, age must be an integer, and that's the case, right? So in that case, we can successfully validate the document. And again, in memory, I'm going to have an actual integer or even int if you want to optimize things, right, in memory. What's very important here is, even if 142 were quoted, that would be fine too. It's all about the literal. You're looking for 142 for digits. It can be quoted, unquoted, it doesn't matter, right? So for validation purposes. So it would also have accepted the document with age quote 142 quote, because the lexical representation that is inside that string is corresponding to the type integer. For whom is that clear? All right. Good. Then I have Booleans like this. Physis is true. It's valid against Boolean, so it works.
We have a question. For a schema where a exclamation is part of a valid key inside the schema, how would be specified a cardinality?
Oh, there is no cardinality here, right? Because there's one key. Let me see the question. So this exclamation mark is only a way of saying it's required, right? Oh, I got it. I got the question. Here's what you mean. You mean we are using the exclamation mark as a special character here. What do we do if I really want a key that has an exclamation mark in the instance? That's your question, right? I imagine. In that case, you move on to the verbose syntax. The syntax you see here, it's called the compact syntax. It covers 95% of the cases in this way. And if you need to really have a key with an exclamation mark, then you wouldn't use the compact syntax. It's rare. And if that happens, then there is a verbose syntax. I will show you a slide to see how it looks like. But now I'm just focusing on the compact syntax. But the short answer is you can also build a schema if there is an exclamation mark in the key, right? And I realize I said there is no cardinality, but yes, there is. You can either have required or optional, right? It's just that you cannot have more than one here, but you could consider this cardinality, of course. Okay, integer. Here we have physis is true, and that's a Boolean, so this is also valid. Note that also if I had quotes around true here, that would still be valid. It would still have been accepted because we care about the lexical representation, regardless of whether there are quotes or no quotes. Okay, the same for null. Here I just require it to be null if I consider it a type. I just added a list that is slightly longer, so there's also the one I gave you here, right? So this list right here. But here, just so you know, there's also more types. You have positive integer, negative integer, non-negative integer, and so on and so on. So you really have a lot to pick from. This is all standardized, actually coming from a W3C specification, right? So the standardization body aligned with XML schema. So these are types here and here, right? I'm just putting them for your reference. Is there another question?
Yes, for slide 75.
Oh, I don't have the same numbers here because I removed the slides of yesterday. Which slide is this?
The question is it still valid if location is required?
Oh, the location here. Yes, it is valid because location is a key associated with the value null. and we are expecting location null, right? You could also remove location null because there's no exclamation mark, so it's optional. So it would also have been valid without location null and without last Einstein also. Right? Does it answer your question? Yes? Yeah, there is no order. So you can absolutely swap the keys and that's still fine because it's really the semantics of the map. So the order really doesn't matter. In practice, I mean, there is theory in practice. It doesn't matter, but very often in practice, when you have a data set like that, it will typically be in the same order. And the reason is simple, is that it's typically generated by codes, right? So if you generate a million objects with the same code, it will just put it in the same order. But technically, it doesn't matter. All right, what if there is?
What if there is a required key inside an object that is not required?
A required key inside an, I'm not sure I understand.
So if you have an object and then within that object you have a key that is required, but the object itself is not required.
Oh, then that's fine. So the require, this exclamation mark here really only applies to that key right here. If it's part of an object that is itself nested in a larger one, and that object, the outer one, is not required, then it's fine, right? It's only required if the object exists. In every object that exists, it's required. Yeah.
And there's one more.
Yeah.
How would you specify a typing union like null or string?
You need the verbose syntax. You can do that. I didn't have slides for that, but you can also have the union of types. You can say it's either a Boolean or an integer, for example. And that is typically something you can do as well. All right. Awesome. So I'm throwing in more types here. You see you have date, timestamp, date, time, date. G, year, month is to just say, for example, November 2022 is a G, year, month. Duration, year, month duration, datetime duration, hex and base 64 for the binaries I told you. So this is just a restaurant menu, and you have all of these types to pick from, right? So of course, there are some that you will use all the time, like string, integer, and so on. And there are some of them that you will use rarely, but they are still here. All right. There is also a way to be very permissive. Yes, go ahead. 2 questions, yeah.
Can you have extra keys?
Yes. Yeah, you can allow that. Here it's not allowed, but you can allow it, and I will show you how. Right? I also actually let me just do it now so that you see. It's this with the verbose syntax. You can basically have, so let me show the verbose syntax since I promised it earlier. This is the verbose syntax. It's a bit more verbose, but in fact, it's paradoxically simpler. Because here we say it's a kind of object. The base type is object, meaning the super type is directly the top level object. Content is the list of all the keys and values. So we say the name is last, the type is string. And this is why you can put exclamation marks now here without any problems. Name first, type string. And then we say closed false. And when I say closed false, I'm explicitly saying it's fine if there are more attributes, right? And then these are more keys, I mean, if there are more keys. And then these keys, you can associate them with anything you want because it's extra. So the schema basically restricts for last and first, that they must be strings. But the other attributes, the other keys, they are unrestricted. You can do what you want. But this is not the default, right? This here explicitly say closed false. If you don't put it, it's actually closed. It's true, and you don't allow extra keys. And so in that case, you wouldn't be valid if you had more keys, but that's just because it's the default, right? So again, there's this idea that very often you actually want to close your objects, right? When you have data frames, we will see later, you do want the objects to be closed and to not allow for extra keys. This is really covering 95% of the cases. And if it doesn't, then you just switch instead to the verbose syntax that has more possibilities in there.
We have another
okay. And the other question, yes? No, it doesn't. The reason is that it's based on the literals, the lexical representation. And so in that case, in the case of the type in JSON, it's really true and false that are the literals. it wouldn't be necessarily true in all languages. It might be that there are some that accept 0 as false and 1 as true. I think in PostgreSQL, for example, that's the case. If you put 0, it's acceptable as false and so on. So this is really something that you need to be flexible. It depends on the actual schema technology you use. So you just need to look at the documentation, right? Okay. All right. Now, yeah, what if we want to be permissive? What if I want to say location can be anything, right? Anything I want. In that case, it's an array with 2 strings. Then you can just use item. Item is just the super type of them all, right? It basically means anything. Then I can have arrays. And with this compact syntax of JSON, the way you validate an array, you use exactly the same syntax with the square brackets. So in the schema, you say ARR is an array of items. It means it accepts anything in the array. And here you have this array of items. You can also be more specific and say ARR is an array of integers, and then you have an array of integer over there, right? So you see the schema is really intuitive to write, or it's supposed to be intuitive to write compared to the documents, right? Then you can also have arrays of objects, right? So here I have nested objects, and I'm saying in the schema that ARR is an array, and it contains objects, and all of these objects, if they have a key foo, it's optional by default, remember, but if they have a key foo, it must be a Boolean. And here I have an array of 2 objects, foo true, foo false. For whom is that intuitive, the correspondence between the two, right? Okay, it's very similar, right? It's very visual, basically. And an empty object would have been fine too, because as I said, it's optional by default if you don't have the exclamation mark. So this I have answered. Now you ask the question. So extra fields are forbidden by default, and you can switch. This is exactly the same thing, basically. This is the compact syntax. This is the verbose syntax. They do the same thing. And then you can just, in the verbose syntax, say that you open the object. And in that case, this year 1905, it's not in the schema. In the contents, there is no such year, but it's accepted because we opened the type. It's called an open object type. Okay. All right. Note that this is something you don't have in many object-oriented programming languages. In Java, you can't have that. I think in JavaScript and Python, you can have extra fields that you didn't model. So you see, it's also kind of tied to programming languages, these sort of things, right? So what do we have? Just to show you the sort of features that you have, it's a summary of what we've seen in general based on JSON. You can restrict value to a specific type. You can say the key foo must be an integer. The array must contain only integers. So you can restrict in this way. You can also...
Is it possible to set the length of the array?
Yes, it is. In the verbose syntax, you can also do that. You can say my array must have between 3 and 5 elements. You can also do that. Yep. You can also cast, for example, you can accept a literal that is in a string, and when you validate and annotate, you will cast it to an integer or a date. You can require a value, so you can say I accept foo true, but I don't accept if foo is missing. That's the exclamation mark in my compact syntax. I can also allow more keys than what is in the schema. So that's called an open object type. So I would accept or refuse, depending on what I want, an extra key, bar, for example. You can also, that I didn't show you, but you can also specify a default value. So you can say, if my object doesn't have a key foo, then please add it when you annotate, please add the key with that default value, right? That's also something you have in relational database management systems. So you can do that. You can even have primary keys that I'm not showing you how it works, but basically if you want to restrict that foo must have unique values, and in that case, there's twice the number 2. So you could reject that based on the notion of a primary key, right? This is all we can do with schema validation languages. JSON, again, is for teaching that it was made. Next week, I will show you JSON schema. You will find it very easy because it's just yet another language, but it does the same things. And then we'll see XML schema, a small part of it, because don't worry, I will not inundate you with the complexity of it, but it's just so that you have seen it a little bit. All right. So I think that's it for today. Just checking before you go that you followed what I've been telling you. And I will give you a link I have it actually on the slide. If you look at the slides and open it, there is an online page where you can actually write your schemas and your instances. Click on a button, and it will tell you if it's valid or not. So if you want to play with JSON, you can. You can just go to that page, right? All right, so we have a majority between 80 and 99, so that's perfect. So next week, JSON schema, XML schema, data frames. I'll show you how that all is connected to data frames in the end. And then we'll move on to MapReduce. So thank you very much, everybody, and see you next week.